When astronomers first detected Proxima b, a planet circling the faint red dwarf Proxima Centauri just over 4 light-years away, the discovery sent waves through the scientific community. For the first time, we had found a rocky world orbiting the nearest star to our own, and sitting in the zone where liquid water could exist. The distance alone makes it extraordinary, a cosmic neighbor close enough that we can imagine, one day, sending something there. But proximity is only part of the story. Proxima b receives almost the same amount of energy from its star as Earth does from the Sun. That balance raises a thrilling possibility, that somewhere on its surface, water might flow. Yet orbiting so close to a red dwarf brings serious challenges. Proxima Centauri is an active star, flaring frequently with powerful bursts of radiation. Such flares can tear away a planet's atmosphere unless the planet has a strong magnetic field to hold it in place. Without that shield, any water would evaporate into space, leaving a lifeless, scorched world. But nature is rarely simple. Some models suggest that Proxima b might be tidally locked, with one hemisphere forever facing the star and the other trapped in eternal darkness. Between those extremes could lie a narrow, twilight band called the Terminator Zone, a region where heat and cold balance just enough for liquid water to survive. This dim, eternal dusk could be a refuge for life. Imagine landscapes of rock and dust where moisture condenses in the half-light, perhaps home to hardy organisms evolved to thrive beneath a crimson sky. If Proxima b retains even a thin atmosphere, winds might circulate warmth around the globe, widening that habitable strip and softening the extremes of temperature. To test these ideas, scientists have turned to the James Webb Space Telescope. Webb's infrared eyes can analyze the faint light from distant stars, revealing the chemical fingerprints of gases in an exoplanet's atmosphere: oxygen, methane, carbon dioxide. Molecules that could hint at biological activity. The presence of these gases in the right ratios would be a clue, but not proof. Methane, for instance, can come from both living systems and volcanic reactions. Every potential biosignature must therefore be tested against natural explanations before the word life can even be whispered. There's another complication. Proxima b does not transit its star from our point of view. That means Webb can't study starlight shining directly through its atmosphere. Instead, astronomers must rely on indirect methods, tracking the star's tiny wobbles or analyzing reflected light so faint it borders on the invisible. To help bridge that gap, new ground-based observatories like the extremely large telescope in Chile are being built, equipped with advanced spectrometers capable of detecting the smallest atmospheric clues. These instruments could one day map Proxima b's temperature, surface composition, even its weather. At the same time, projects such as Breakthrough Listen are using giant radio dishes to scan the Proxima system for any artificial signals, regular pulses or structured transmissions that might reveal technological activity. So far, nothing conclusive has emerged, but given how close the system is, scientists continue to listen. The search for life there also raises profound questions. If something lives on Proxima b, what would it be like? On a planet bathed in red light, photosynthesis might depend on infrared radiation instead of sunlight. Plants, if they exist, could appear dark, almost black, to capture every trace of energy. Other forms of life might dwell underground or beneath frozen seas, shielded from radiation in hidden oceans warmed by internal heat. Here on Earth, we've already learned that life is astonishingly adaptable. Microbes thrive in boiling volcanic vents, acidic pools, and even inside rocks buried beneath Antarctic ice. These extremophiles prove that biology can survive without sunlight, oxygen, or mild conditions, drawing energy directly from chemical reactions within stone. If such resilience exists here, it might also exist there. Proxima b may host subsurface lakes or hydrothermal systems, providing safe havens where microbial ecosystems could emerge. Even if they look nothing like Earth's life, they would still mark a second genesis, evidence that the universe itself is fertile. The planet's discovery has also reignited the dream of interstellar travel. Because it lies only 4 light-years away, Proxima b is a plausible destination. Projects like Breakthrough Starshot envision fleets of ultralight probes driven by powerful ground-based lasers. When astronomers first detected Proxima Centauri b, a planet orbiting the dim red dwarf just 4.2 light-years from our Sun, the news rippled through the scientific community like a spark across dry grass. For the first time, humanity had found a potentially Earth-sized world in the nearest star system to our own. A planet close enough, in cosmic terms, that we could almost imagine visiting it within a single lifetime. Proxima b quickly became a symbol of possibility. It lies within the habitable zone, the narrow orbital region where temperatures might allow liquid water to exist. In theory, oceans could shimmer under its faint red sky, sustained by the gentle warmth of its parent star. But around red dwarfs, gentle is rarely the right word. Proxima Centauri is a restless star, prone to violent magnetic storms that hurl flares thousands of times more powerful than any our Sun produces. These outbursts bathe nearby planets in deadly radiation. If Proxima b once had an atmosphere, such storms might have eroded it over eons, stripping away the shield that makes life possible. Yet, scientists aren't ready to give up hope. With a mass roughly 1.3 times that of Earth, Proxima b could possess a molten metallic core capable of generating a strong magnetic field. Such a field might protect its atmosphere from being completely lost to space. If even a portion survived, conditions on the surface could vary dramatically between extremes, scorching heat on the day side and freezing darkness on the night side. Because Proxima b likely keeps one face permanently toward its star, a state known as tidal locking, one hemisphere may be bathed in endless daylight, while the other remains shrouded in perpetual night. But along the thin boundary between the two lies a twilight band, a region astronomers call the terminator zone. Here, temperatures could balance in a delicate harmony, cold enough to preserve ice, warm enough for liquid water. If life exists there, it might inhabit this eternal dusk, thriving in conditions unlike anything on Earth. Imagine a landscape of dim red light, where the sun never rises or sets but hangs forever on the horizon. Rocky plains stretch into mist, and thin clouds glow crimson against a darkened sky. If microbial life had adapted to such a world, it would likely look nothing like us, perhaps feeding on infrared energy, or drawing nourishment from chemical reactions deep underground. To search for such clues, scientists turn to the James Webb Space Telescope, humanity's most advanced eye in the cosmos. Webb can detect faint patterns in starlight that reveal the presence of atmospheric gases, oxygen, methane, carbon dioxide, chemical fingerprints that might hint at biological activity. But there's a challenge. Proxima b doesn't cross in front of its star from Earth's point of view, meaning Webb cannot directly observe light filtering through its atmosphere. Instead, researchers rely on indirect methods, measuring the subtle wobble of the star or studying faint reflections of light bouncing off the planet's surface. New instruments under construction, such as the extremely large telescope in Chile, will soon join the effort. With mirrors spanning more than 30 meters, they will probe nearby worlds in unprecedented detail, perhaps revealing clouds, continents, or even seasonal changes on planets orbiting other suns. The search has also expanded beyond optical astronomy. Radio observatories across the globe are now listening for signals, repeating patterns or narrowband transmissions that nature rarely produces on its own. The Breakthrough Listen initiative has already targeted the Proxima system, hoping to detect the faint whisper of technology from a neighboring civilization. So far, the skies remain silent, but silence itself is data, a reminder of how rare and precious intelligence may be. Still, the proximity of Proxima b makes it a natural target for the next great leap, Interstellar exploration. Projects like Breakthrough Starshot envision fleets of miniature spacecraft, each no larger than a computer chip, driven by powerful Earth-based lasers. Accelerating to a fraction of light speed, these probes could reach the Proxima system in just a few decades. If successful, they would transmit back humanity's first close-up images of an alien planet orbiting another star. A dream once confined to science fiction could soon become our next great experiment. But excitement is always tempered by caution. Even if Proxima b resides in its star's habitable zone, that doesn't ensure it's truly habitable. The constant exposure to stellar winds and flares might have sterilized the surface long ago. And if its atmosphere is gone, life may survive, if at all, deep beneath the ground or hidden under frozen oceans, protected from the radiation above. Yet optimism endures, because every discovery about Proxima b reshapes our understanding of what life can endure. On Earth, we've found extremophiles thriving in boiling volcanic vents, beneath Antarctic ice, and inside radioactive mines, organisms that rewrite the limits of survival.